Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
I'm Drew, and today's episode is about photonic computing, a new kind of technology that replaces electrons with light. Every message you send, every video you stream, every AI model that tries to guess your next word, it all runs on electrons. They're the lifeblood of the digital world, racing through microscopic circuits billions of times every single second. But there's a problem. We've pushed them to their limits. Modern processors are so densely packed that they're starting to cook themselves. The faster we try to move electrons, the more heat and energy they waste. Right now, data centers that power the internet consume as much electricity as some entire nations. And with the explosion of artificial intelligence, that energy demand is skyrocketing. For decades, computing power followed Moore's law, the idea that the number of transistors on a chip doubles every 2 years. But physics is catching up with us. Transistors can't shrink forever, and electrons can't move any faster through silicon without running into the laws of thermodynamics. We're hitting a wall. And that wall is a real problem for AI. Training models like ChatGPT or Google's Gemini takes weeks and burns through enough energy to power thousands of homes. The cost of intelligence, at least in the digital world, is starting to look unsustainable. So here's the question. What if we could process information not with electricity, but with light itself? Photons, the particles of light, don't collide with each other. They don't generate resistance, and they travel at the fastest speed that the universe allows. Instead of forcing electrons through wires, what if we use beams of light to think, to compute, to learn? That's the promise of photonic computing. Circuits that use light to calculate, reason, and maybe even reshape the future of artificial intelligence. Before we dive into how photonic computers could change the world, let's first understand what they actually are and how they work. And to do that, we first need to take a step back and start with what a normal computer does every second of its life. Traditional computers use electricity. Inside your laptop or your phone, billions of tiny switches called transistors control the flow of electrons through microscopic wires. Each transistor can be either on or off, representing the familiar binary code of ones and zeros. Every image, song, or AI response you've ever seen comes from nothing more than trillions of these electronic flips happening at incredible speeds. Photonic computing keeps the logic, but it changes the medium. Instead of using voltage, it uses photons, particles of light, to represent and move information. A single photon can carry a bit, a 1 or a 0, but it doesn't have to stop there. Light can be tuned and shaped in many ways, by changing its wavelength or its color, its phase, the timing of its wave, or its intensity, how bright it is. Those properties become the language of information. Think of it like this. Where electronic computing speaks in Morse code, photonic computing speaks in full sentences. But why use light at all? And that's because photons are astonishingly efficient. They travel faster than electrons, and they don't create heat by bumping into things. There's no electrical resistance, no wasted energy, no need for the huge cooling systems that plague today's data centers. And here's the powerful part. Multiple photons of light can move through the same space without interfering with each other. This is called multiplexing, and it's like giving every color of light its own highway lane. Instead of traffic jams of electrons, you get a wide open sky full of parallel beams, each carrying different data streams at once. That's where photonic computing gets its massive speed advantage. It's not just faster because light moves quicker, it's faster because it can process many things at the same time. The physics behind it is elegant. By precisely guiding and bending light through microscopic structures, scientists can generate logic operations similar to the traditional AND or NOT gates in an electronic chip. They use principles like refraction, how light bends when it passes between materials, and interference, where two light waves combine to amplify or cancel each other out. Even total internal reflection, same trick that keeps light trapped in fiber optic cables, helps route signals through these tiny optical circuits. We already use light to move information across continents through fiber optic internet. Photonic computing takes that to the next step. We've mastered sending light with these super useful fiber optic cables. Now we need to use light within our very own computers to run our daily lives. All right, so now that we know the why, let's dig into the how. Because saying we compute with light sounds futuristic, until you realize the people are actually doing it right now. Here's the catch. Light doesn't have charge. It can't be switched on and off like an electron. So traditional transistors, the foundation of modern chips, don't work. To build a computer that runs on photons, engineers have to reinvent the building blocks of logic from the ground up. Let's start with the core components. Waveguides are the light equivalent of wires. They're microscopic channels carved into a chip that guide photons along precise paths for light. The idea comes from fiber optics, but scaled down to fit inside processors thinner than a human hair. Then there are lasers. These are the engines of the system. A photonic chip needs steady, coherent source of light. Essentially, a miniature laser built right into the circuit. Next, we have modulators. These are the devices that change some property of the light. Maybe its brightness, its wavelength, or its phase, to encode information. It's the optical version of flipping a transistor from 1 to 0, but done by bending or filtering light, rather than pushing electrons. On the other side, there are detectors, which do the reverse. They read the modulated light and convert it back into electronic signals when needed, allowing photonic and electronic components to communicate seamlessly. Once you have these parts, you can start doing logic, the foundation of all computation. Optical versions of the classic and or not logic gates are often built using something called a Mach-Zehnder interferometer. Picture a beam of light entering a path where it's split into two, put through modulators, and then recombined. Depending on how the waves line up after that splitting process, they either amplify each other or cancel each other out, either a 1 or a 0. That's a logic operation, performed entirely by the physics of interference. No electronics required. Thousands of these interferometers can be arranged on a single chip, performing vast amounts of math in parallel at the speed of light. Of course, it's not purely optical yet. The most advanced systems today are hybrid systems. They combine photonic logic for ultra-fast processing with traditional electronic components for memory and control. Think of it like a hybrid car. Electricity for efficiency, gasoline for range. The mix gives us the best of both worlds, while light-based memory systems and fabrication technology are still catching up. Speaking of fabrication, one of the big breakthroughs has been silicon photonics, a way to make light-based chips using the same tools already used for traditional silicon electronics. By layering optical materials onto existing chip wafers, researchers can produce photonic circuits with far less cost and far less complexity than before. Other materials, like indium phosphide or lithium niobate, are even better for manipulating light, offering improved speed and lower energy use. Though, they're harder to manufacture, partially because of the massive infrastructure for silicon materials. The race now is to find the right balance. A material that's efficient, scalable, and affordable enough for mass production, while being efficient for light. The advantages are undeniable. Photonic chips can transmit and process data with almost no heat, far less power usage, and they can handle multiple data channels through different wavelengths simultaneously. In terms of energy per operation, light-based computing could outperform traditional chips by orders of magnitude. In short, photons don't just move fast, they move freely, and that freedom might be exactly what we need to break past the limits of silicon. This might sound like high-end lab research, and it is, but the motivation is deeply practical. Our world is drowning in data, and traditional electronics are reaching their breaking point. Photonic computing isn't just a distant dream. It's a necessary evolution. And the reason people are so excited about it isn't just because it's fast. It's because it solves a growing crisis in how we use energy. Right now, the digital world runs on power. Every time you upload a photo or ask an AI to write something, it takes electricity, sometimes a lot of it. The data centers that handle all this already consume a few % of the world's total electricity, and the demand keeps climbing. Training large AI models has become one of the biggest energy drains in history. A single training run for a cutting-edge system can use more power than hundreds of homes do in a year. The smarter our machines get, the hungrier they become, and that's not sustainable. Photonic computing offers a way out of that spiral. Because photons don't generate heat the way electrons do, they waste far less energy. A light-based processor could run cooler, faster, and for a fraction of the cost. Scaled properly, that could mean data centers that use a tenth of the electricity, and maybe even small devices that can handle AI without draining their batteries. There's also the issue of scale. For decades, the idea of technological innovation was this: make transistors smaller, fit more of them on a chip, and you'll get more power. But we've reached a point where shrinking further isn't practical. Electrons start leaking through barriers, and the chips get too hot to cool efficiently. It's like trying to pack more cars onto a highway that's already bumper to bumper. Photonics changes the game by giving us an entirely new kind of scalability. Instead of relying on smaller transistors, we can pack more information into each signal by using different wavelengths of light. It's like opening up new lanes in that traffic jam, except now they're stacked vertically, and each one is moving at light speed. The potential bandwidth is enormous. Optical channels can carry multiple streams of data in parallel, and that could make supercomputers thousands of times faster without needing more power. That also means smaller, more efficient processors for the devices that we use every day, like smartphones and laptops. But the impact goes beyond speed again. Energy efficiency has environmental consequences too. Data centers are among the fastest growing sources of carbon emissions. A shift to light-based computing could ease that burden, cutting down on cooling systems and energy use while keeping the same level of performance. In the long term, that could make AI and cloud computing genuinely sustainable. There's also a ripple effect. Faster, cheaper computing could accelerate everything from climate simulations to drug discovery. It could make high-level AI tools more accessible to universities, startups, and countries that can't afford massive data infrastructure. The benefits compound when the cost of intelligence drops. This isn't just about creating faster machines. It's about keeping the future of computing open, so progress doesn't collapse under its own energy demands. And that leads to the next big question. What can we actually do with all this? What new possibilities open up once light becomes the engine of computation? The good news is that this isn't a lab curiosity anymore. The first generation of real photonic processors is already out there, and the results are looking incredible. AI is one of the areas that's most driving this excitement. These AI systems rely on something called matrix multiplication. Huge grids of numbers that get multiplied over and over to find patterns. It's the foundation of how neural networks work. These operations are massive, and they're what's making AI training so energy intensive. Photonic processors can handle those matrix calculations using light interference instead of electrical current. Companies like Light Matter and Luminous Computing are already building chips that do this. The speed is impressive, but again, the efficiency is that much more important. A job that might take days or weeks on traditional processing could be done in hours with a fraction of the energy. AI models have become faster to train, cheaper to run, and small enough to deploy locally, instead of relying entirely on giant data centers across the world. That means more experimentation, more accessibility, and a lower environmental cost. The next area is data infrastructure. Right now, the physical connections between processors and data centers are a major bottleneck. Electrical signals lose energy as they travel, and the systems that keep those machines cool eat up a ton of power. Optical interconnects, cables that move data as light instead of electricity, solve both problems at once. They reduce latency, cut heat, and allow far higher data throughput between servers. In the long term, that could mean faster internet speeds, more reliable cloud services, and data centers that use much less power. Considering that cloud computing already rivals the airline industry in carbon emissions, that's a big deal. Then there's healthcare. Photonic processors could supercharge the computations behind medical imaging, from MRI scans to high-resolution imaging. These systems depend on algorithms that require huge amounts of math, exactly what light-based chips are great at. Faster processing could mean clearer images, shorter scan times, and earlier detection of disease. Beyond imaging, photonic computing could help simulate biological systems in real time. Things like protein folding or drug interactions that currently take supercomputers weeks to model. If that process can be done faster and cheaper, it could change how we discover and test new medicine. The benefits also reach space and communication technology. In space, energy and weight are everything. Photonic chips are lighter, faster, and more power efficient, which makes them ideal for satellites or deep space probes. And because they don't generate much heat, they're easier to cool in the vacuum of space. There's also the promise of fully optical communication systems, where light isn't just a signal between computers, but the method of processing inside them too. That would make space networks faster and more resilient, with less power required per bit of data. And of course, this technology could eventually reach everyday devices. Imagine phones or AR glasses that can handle complex AI tasks instantly, without connecting to a cloud server. You could have real-time translation, image recognition, or even small-scale generative models running directly on the device, all using less power than today's processors. That would also mean sensors that can think locally, drones that analyze their surroundings without constant internet access, or medical wearables that interpret biological data as it's collected. Each of these applications points back to the same idea. Light gives us room to grow again. We spent years optimizing electronics to their limit, squeezing out every possible improvement in speed, efficiency, and size. Photonic computing opens a new dimension of progress. But breakthroughs like this never come easy. The technology is still developing, and there are real obstacles to overcome before it reaches its full potential. That's what we'll talk about next. The challenges that stand between light-based computing and the future it promises. First, there's the issue of scale. Light has a wavelength measured in hundreds of nanometers, while modern transistors are just a few nanometers wide. Building circuits that guide photons at this tiny scale requires a completely new design, often at the quantum level. Integration is another hurdle. Mixing photonic components with electric ones isn't easy. Aligning waveguides, lasers, modulators, and detectors with nanometer precision is difficult and expensive. Even the tiny misalignment can lead to signal loss, slowing performance, or creating errors. Materials are a critical challenge as well. Silicon, the backbone of traditional chips, isn't ideal for manipulating light. Alternatives like indium phosphide or lithium niobate work better, but are costly and harder to manufacture at scale. Finding affordable, scalable materials is essential for widespread adoption. Then there's data storage. Photonic chips can process information at incredible speeds, but they still rely on electronic memory for storing data. True all-optical memory remains a research goal, and until it's solved, hybrid systems will dominate. Finally, there's the software side. Even if hardware exists, programmers need frameworks, compilers, and libraries to take full advantage of photonic capabilities. Developing these tools will be critical to turning lab prototypes into usable technology. Despite all these challenges, progress is rapid. Labs around the world are building faster, more efficient photonic chips every single year. Each breakthrough brings us closer to a future where computing isn't limited by heat, resistance, or energy consumption. Photonic computing represents more than just faster processors. It's a shift in how we think about computation itself. For over a century, we've relied on electrons, chasing the goal of squeezing circuits into ever smaller chips. Now we're teaching light to carry logic, to perform calculations, and to expand the limits of what machines can do. Light has always symbolized discovery, from Newton's original experiments with prisms to the lasers and fiber optics that connect the world today. Photons have helped us see, measure, and understand. Now they're becoming active participants in computation. The potential is enormous. Faster AI, greener data centers, advanced medical simulations, and more efficient communication could all emerge from the circuits that compute with light. And beyond the tech, there's a human story here. The story of curiosity, persistence, and creativity, pushing physics into the next new territory. We're watching a revolution in real time. The next breakthroughs in AI, medicine, energy, and science might not come from stronger machines, but from the elegance of physics itself. Photons, moving at the speed of light, are beginning to think, and they may redefine what it means for humans to solve problems in the 21st century.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.